All right, hi everyone. I'm Alexander. I'm a senior staff engineer at Cruise, and today I'm very humbled and excited to present to you, together with Anne, our staff engineer, our Cruise.data system, which is a new dataset processing pipeline for CruiseML. And here's our agenda for today. We'll start from discussing what are generic needs for data processing for machine learning, and for ML practitioners, what are existing open source systems available to them, and what are areas for improvements in that status quo. And then Anne is going to walk you guys through Cruise.data solution, and last but not least, how Ray makes it effortless to build. So let's start. These are general data processing needs for machine learning. You have mainly two kinds of data transformations. One kind of transformations, in the context of this presentation, we will be calling offline transformations. So data processor step would normally take a few datasets in and produce one or few datasets out. And there is another kind of transformations we'll be calling online that happen during training. Again, people might be calling things online in different contexts in different way. But here, in the context of this presentation, online transformations would be transformations that run during training. And in there, you also would be taking a few datasets in, or maybe just one, and doing something with them, like combining in a certain way, and then having this unified data stream and feeding into your model training loop. And in the end, training gives you a model. And there is generally no clear rule for ML engineers where to put those transformations, in online setting or in offline setting. Majority of transformations actually can be put in any place, things like concatenation, interleaving of datasets, and any other forms of sampling. They can be also per row level sampling. Applying transforms on a per row basis, such as just a map function, filtering rows, batching rows, shuffling your dataset or segments of datasets, and so on. And it's not just confusing where to put that logic, but also, once you do that, it can be also challenging to change that choice. And we will look in more detail for the reasons why on the following slides. So what is our opportunity for improvement here? First of all, we have fragmented offline and online data transformation systems, and there are just too many datasets to manage. And on top of that, we have inefficient data reading and loading in training that I think many teams in the industry suffer from. Generally, people trying to use GPUs for training, they would really expect for loop in training to be getting next mini batch of data as soon as it wants to have that mini batch. So you really need to hide latencies of data reading and data transformations. And in order to do that, you would be maybe prone to, let's just throw capacity in a problem. So we'll try to use a host with more CPUs, with more memory, try to hide latencies really well. Like you would need some large memory buffers potentially for that. And actually what we discovered is that by trying to hide latencies, we end up spending more money on CPU and memory than on GPUs, which can be quite counterintuitive finding to many people who know, hey, GPUs are expensive. But if you actually try to leverage GPUs well, and you don't have very efficient data loading pipeline, actually the cost dominance shifts to CPU and memory. And on top of that, if you don't go to more complex data loading infrastructure where your data loaders will be separate, in a more simplistic case, there is also a limit to how much memory is available to you. So you would be seeing, let's say, frequent ooms. And generally speaking of reliability, it's hard to debug training data loading failures. Another sort of problems, is there is no parity guarantee between transformations that happen offline and those that happen in online training setting. Maybe in one case, you preprocess your data and save it in a data set, and in another case, you just decided to do it on the fly and assumed the logic is the same, but maybe there was a small bug. And in the end, it would be just really challenging to debug. Most likely, you would be misled in your experimentation and take wrong conclusions. It can be really costly and cost maybe several months of development. That would be a big problem. And of course, there is more traditional machine learning challenge of parity between offline transformations in general that either happen as pre-processing stage before training or during training, and online inference transformations. For example, feature extraction parity. So these are our areas for improvement. And we'll be looking later in the presentation how our Cruise.data system attempts to solve those. On top of this all, there are some use case-specific challenges that are not really specific to autonomous vehicles, but they're more dominant in autonomous vehicle space. So first of all, we're dealing with high-resolution sensoric data. And this leads to larger data sets, larger memory consumption during data loading. And many people might be familiar with a training regime where you would be seeing every example just one time. This is popular in large internet companies with abundance of labeled data. But in our case, we need to do multi-epoch training with shuffling, and data is read and transformed every time you go through the data, and every time it's done in different order. So these things, they really make naive approaches to caching challenging. You can't just say, hey, every distributed training worker is going to store a pre-processed version of the data set and make it really easy available to read. And as a result, caching just ends up being infeasible in a simple form. And we will discuss more complex versions of caching that actually work in a later part of our presentation. And last but not least, there is this so-called need for analytical queries, SQL-like queries into data sets. For example, people might want to check distributions of their data. They want to mine some interesting examples, some scenarios where models don't do as well. And typically, data formats that are meant for efficient data loading during training, they end up being not friendly to those kind of analytical queries. So people end up storing two versions of those data sets. The issue here is that there is no system to keep them consistent. So again, you have this parity challenge. So let's first quickly look at existing online systems that would be used during training. So generally, these systems, they are easy for ML engineers to use and test locally. They promote local debugging flows, notebooks, visualization, and so on. And in PyTorch world, that would be ecosystem of data pipes, data loader, and Torch.data for those familiar with this ecosystem. New Torch.data package, which was introduced within last year, I think, brings much more structure to traditionally less structured PyTorch ecosystem. But it still uses PyTorch data loader with multiprocessing to parallelize reads and transformations, which prevents buffers reuse in readers. And this generally leads to higher costs and out-of-memory error chances. And most engineers I worked with, they just have hard time debugging profile Python multiprocessing applications. There are some people who can be really efficient in this, but just even Linux tooling is just not really good at it. And if you're dealing with a single process with multiple threads, all those tasks become much simpler. Now, additionally, it might seem appealing that in PyTorch ecosystem, in data loading, you can put arbitrary Python in your data loading logic. But what we discovered for autonomous vehicle research and development and production ML engineers, actually putting some small guardrails in place that would actually enable them to experiment faster and get results done in a small amount of time, because they end up running training in a more reliable and in a faster fashion. And there is also this interesting detail we discovered with PyTorch data loader, that the way it enforces deterministic data loading in training, it is actually having very significant performance cliffs in some rare scenarios. And sometimes we've been sufficiently unlucky to hit those rare scenarios, the way readers and their latencies align with each other. Now, in the TensorFlow ecosystem side, there is a package called tf.data. From performance and efficiency of the library perspective, it's a very mature one, and it has many knobs. For example, it has deterministic and non-deterministic modes of loading, and it connects really good with TensorFlow ecosystem, but doesn't connect that well with PyTorch ecosystem. And this is kind of deal breaker for us. And people might say, hey, maybe you just use both together. But for people who try to combine PyTorch and TensorFlow in a single process, especially in a more unified build settings, they know it's can be very challenging and just expensive to maintain support for two deploying frameworks within a single deployment. And last but not least, Python transformations are not executed as efficiently in TensorFlow world. They would be hitting global interpreter lock. in that multi-processor, multi-threaded executor that they have. At least last time I looked, it was the case. And in offline systems, switching gears to those, we have things like Apache Beam and Spark, and they're really flexible and can be very performant and scalable. But they may require a lot of boilerplate for simple things, such as like writing a pipeline and writing some preprocessing stage that creates a new data set and then feeding that into trainer. And they're usually not very well known by ML engineers, ML practitioners familiar with TensorFlow or PyTorch. And there is this practical consideration. In many cases, deployments of such systems don't have GPU access. So what is our ideal scenario? Before we go into solution phase, we would like to be able to prototype in online setting to be able to perform transformations during training. And once ready, we should be able to move parts of transformation graph that is movable to offline setting. Things like filtering and deterministic map operations are good candidates to be moved to offline world. But we will keep some operations online, such as all sort of sampling operations. Sampling can be done on the level of data sets, on the level of rows. And people just like to change parameters in their data distribution and experiment actively with that. Regenerating data set every time you want to change some sampling configurations usually is just not efficient for ML practitioners. And things like batching, random data augmentation, and transforms exploding the data size. They better to be kept online as well. And last but not least, we would like to have inference parity. So all transformations that happen in offline preprocessing or during training, we would like to be able to take them and package together with the model automatically and use that for online inference. So we solve that online inference parity problem once and for all as well. And now I'm going to let Anne talk about our Cruise.data solution to this set of problems.
Yes, thanks, Alex. Now comes to the exciting part. I'd like to introduce you our Cruise.data solution, and I will walk you in depth how it solves the problem that Alex just mentioned. So there are some specialty of Cruise use case. First of all, we are dealing with very heavy columns, so any redundant copy of those columns can result in unstable memory peak during training, and it can lead to ohms and fail the job. Secondly, our users, they do need a lot of flexibility and different ops to support their data transformation logic. Especially for dealing with the AV case, we need to have a lot of support around sampling so that they can have better data distribution, and it's critical for the model performance. Therefore, we develop a bunch of ops for our user to author a data pipeline. They can use different combination of the ops to describe what they want to do with their input data. And the output of the data pipeline is just a graph. It's not executed yet. So this is our DSL layer in Python. So we also provide a stable graph intermediate representation layer. The purpose is to separate the declaration from the execution. So our execution is all on C++ side so that we can maintain the efficiency for memory and also the throughput. This layer can transmit the graph from Python to C++. Other than that, we have good tools to visualize our graph to our user. We also leverage this layer. So there are two executors. For the online part, currently we leverage the Python, the PyTorch data loader to provide multi-processing to make it run more efficiently. Underneath, we have a loader, as I mentioned, it's implemented in C++, so we can leverage the regular threads to do that. Okay, then Ray helps our ecosystem for two parts. One is called graph optimization. The other part is Ray serves as the backend for our offline executors. Both I will go in depth. Before going into that, I would like to give a shout out to our amazing orchestration and compute team. They are able to make us life much easier. To develop a Ray job, we just need to apply a Python decorator by providing the results spec, and this job will work seamlessly with the other jobs in our user pipeline. Those other jobs can be with different backend. It doesn't need to be Ray. So here's the graph optimization problem I just mentioned before. The purpose of that is to rewrite the graph so that our execution can be more efficiently. So there are usually multiple iterations for graph rewriting, so we can focus some purpose for different iterations. There are some cheap and easy graph optimization passes. For example, if such pattern is detected in user-defined pipeline, we can replace it with a more efficient op. For example, if user-defined shuffle, then followed by a batch, we can replace that with a fuse shuffle and batch. Basically, underneath, we can have better memory management with that new op. And some graph rewriting is very expensive. For example, going through all the rows, all the files to build the read index, or for some very advanced sampling algorithm, we need to go through all the rows to generate weight so that we can properly sample them. There are some commonalities about those expensive graph optimization parses. They all need to go through millions of rows with terabytes of data, and they all need to finish very quickly because the graph optimization belongs to our data loader initialization stage. If running with training, our expensive GPU nodes are set idle to wait that phase to finish. So here we set a SLA at 5 minutes to finish the graph optimization, no matter how large the data set is. For some extreme case, if we, for example, expand our data set by 100x, we probably cannot run graph optimization on the fly. Then it should be very easy for us to run it offline and cached. Luckily, we have thousands or even more files, so we can map this problem to an embarrassing parallel problem where we use Ray to speed it up. That's what we did. And we do see phenomenal improvement by applying Ray to make this job run much quicker. You can see with a medium-sized PR, we managed to improve our performance by 100x, and the cluster is still not very large. That's amazing, right? What's even more amazing is, like I mentioned, have a Ray job defined as separately and run independently is super easy for us. So if we need it, we can run it offline. Other than graph optimization, now comes to the offline executor part. So we use Ray as our backend and work with the data loader I mentioned before for the offline execution. It brings us a lot of benefits. First of all, no parity issue at all because we are using the same data loader. Secondly, there's less engineer time invested for developing a feature because once a feature is added, you don't need to modify 2 places to add the same support. It can be leveraged for both passes. And for the offline offload computation part, if a user defines a very complex data pipeline, they can start with that for training and decide to say, I want to offload this part to run offline. And for the online, it should be much lightweighted. So with this offline executor, it works very well. Ray enables us to run at scale. It solves the data imbalance issue for us if we have many more tasks than the physical node. Secondly, Ray helps us to speed up some of the user-defined mapper op that needs GPU acceleration. This is a high-level and simple version diagram of our offline executor, and you will understand why we call it materialization. So basically, for the user input data pipeline, for each task, we append a shard node at the end. So each task is dealing with a portion of data. The data is loaded and transferred based on the user definition, and it's written out immediately. There's no data moving, cobbling involved because the data is written out immediately. And you know, those data cobbling and moving can be very, very expensive. That's why without those, our offline executor runs very efficiently. And secondly, because each job, they are independent from each other, so it enables us to reliably retry a failed job and provide this very good reliability to our end users. Okay, there are some ongoing and future work we plan to improve our Cruise.data solution. Currently, we support our PyTorch scriptable mapper to run in multi-threaded executor. We want to expand that to more Python functions, so it's more user-friendly for our end user. We may explore Torch deploy for that purpose. And currently, once we release the Cruise.data to our users, they are very excited about that, and they come up a bunch of great ideas. So they are sending us requests at the more ops in our ecosystem. And we are also keeping improving our performance. That's the core of Cruise.data. And we also plan to revamp our current production pipeline to replace the old solution with the new Cruise.data solution. For example, bulk inference can be one good candidate. We no longer need another infer to do bulk inference. We can use the user input data pipeline by appending a map to predict on the model and leverage our offline executor to run it at scale. Of course, we will keep improving our data loading logic to make our training more efficiently. We've heard the Ray dataset work like in these 2 days, and we are very excited about the potential opportunity we can collaborate to realize some of great ideas we already have. And the last but not least, we are very interested in open sourcing this solution to more users who are using PyTorch and users who are interested in efficient data loading. Okay, in summary, we are trying to build a novel system for ML data processing. We want this solution to also enable the flexible, efficient, and faster data loading. So it provides the parity, as I mentioned, for cache and on-the-fly transformation. For both modes, it needs the backend to enable this distributed computing to enable it run fast and at scale. So Ray helps us to enable this backend efficiently and in a matter of weeks, not months or quarters. Okay, thank you. Any question? Okay.
Do we have a mic for questions?
Oh, sorry. How do you handle like versioning of data sets and like metadata and discovery of the data sets and versions?
I can take it.
Go ahead.
Yeah. So from the library, for the reader and writer, we don't care about the data version. As far as you can provide us the absolute path of your data set, we can ingest it or write it out. From our higher level, we do have a versioning system for managing the data. So we we build the semantic meaning for the data set and the versioning for those data set. We have the dataset backend, dataset metadata backend to register and manage those dataset. But I would say it's all scope of the pure library, the reader and the writer library, but it does support it in our system.
Maybe to just add on top of what Anne said, we have that orchestration system that we leverage and mentioned, and you can think of, let's say, index builder or materialization as a step in our orchestration stage. And that system can really cache all those functions. There is concept of stable serialization that enables understanding if that function was ever executed with same parameters or not. So in this case, we can know that this materialization was already done. So library would be sufficiently intelligent to redo the work or not redo the work. This doesn't replace some kind of high-level metadata management for data sets, like nice drop-downs with UI, like, hey, these are my data sets. So this is, as Anne said, would be a different layer of abstraction.
Cool, thanks. And you're able to like track lineage of the data as it flows through training and whatever? Or is that part of this system?
So the graph is kind of layered. As Anne described, data source graph, you can add more items to it. And now some of the data processors that you might want to track lineage of, that they would be just doing straightforward operation, just adding something to the graph, not even executing it. That's kind of the beauty of stable IR for the graph. And then lineage is being tracked by orchestration system that we use.
Thanks.
So when do you use Cruise.data, and when would you use Ray datasets? Would I ever use Ray datasets if you open source this?
I would say like those two are from like different layers. So the mission of Cruise.data, one is to support reading data, like single data super efficiently with low memory footprint. And secondly, we support a bunch of operators based on some common needs for data processing. As I mentioned, like sampling or batching or shuffle. Those are like in-house, like we implement those ops on our side. Ray data side to me is like, it's a even more powerful like Torch data loader. You can scale your data reading in another layer. Like for example, you want to run our reader underneath, and then use Ray dataset to distribute the workload across the cluster. So I don't see any like confliction of using those two together. Yeah, that's also like the collaboration opportunity I'm looking for.
What is interesting is also sometimes people try to go to this broad infrastructure or where they would separate data loading from, let's say, trainers. I think we haven't exhausted optimization opportunities within existing training cluster, plus caching that is just completely separate. And once we exhaust those opportunities and we see a need to actually distribute data loaders in live while training, then that's where Ray datasets can come very handy.
So can I interpret this Cruise.data as map functions for Ray dataset that's highly optimized, and then you can also optimize graphs of map functions locally using this graph optimizer?
I think for Cruise.data, currently we focus on optimizing the map function, as you mentioned. But based on our user need, we may also build like some aggregation or reduction capability on top of it. But we want to, at least for our end user, if we want to use Ray underneath, just like materialization, we want to treat it as an implementation details instead of Ray as the user surface, the API. So we will then decide if we want to enable some add some reduce or aggregation capability to our library. We will definitely explore Ray as a backend, but yeah, we will treat that as implementation details.
I saw that out of memory was an issue. What did you guys use to like overcome that? Was it Ray specifically or something else?
Sorry, I don't got.
Could you repeat the question? We couldn't see you. If you could walk in the middle.
How about here?
Yeah.
So I saw that out of memory was an issue in one of your slides. Did you use Ray to like overcome that or something else?
So Ray is used for speeding up some of the heavy operation by providing us this parallelism. And the Ray also used for serve as our backend for the offline executor, as I mentioned. Your question is, do we encounter any issue by using Ray?
So how did you overcome the out-of-memory issue?
Oh, I see. Because for the materialization, the current implementation is you reading the data and you write it out immediately. So we limit the temp object in memory for our implementation. That's how we that's how we make offline executor to work with any large data sets. Secondly, because our implementation avoid copying, that's the core mission of our library. So we do see more stable and for the peak memory during usage. That also helps the out-of-memory issue.
So it wasn't like a Ray solution, rather it's an implementation detail that you guys did, right?
Yeah, that's implementation details, how we use Ray. We pay extra attention to the object that lives in the memory. Mm-hmm.
And also comparing, let's say, to PyTorch ecosystem, which heavily relies on multiprocessing, because we go with stable graph representations that can be executed in C++, we can use threads. And then, let's say, reader objects, they don't have independent buffers. We can potentially have a reader buffer shared with shuffle buffer. There could be a lot of optimization opportunities if you live in a single process that you don't get with PyTorch data loader, as an example.
I had a quick question. As you're pipelining your transformations, are you running these transformations exclusively on CPU nodes and feeding them to GPU nodes, or are you also running them on GPUs?
Yeah, it can be configurable. So some of the processing depends on if the user-defined function can benefit from GPU. Like if we treat inference as a map of course it can benefit from the GPU run. And if the op is just to rotate a graph, maybe it's not. So it's configurable.
And is that configurable because of the ray scheduler, or are you doing that separately?
Yeah, for on the fly. So if things are running on line only, currently we all use CPU. For the GPU part, we do leverage ray for the offline executor.
Okay, thanks.
Just to clarify, like user code has to know, like let's say user puts a UDF, that UDF needs to know how to use GPUs. And I think about our system, let's say again comparing to PyTorch data loader, CUDA just doesn't work, CUDA memory doesn't work well with multi-processing and memory sharing. That is being the case in PyTorch data loader setting. Again, single process, much easier to share memory. Under the hood, we're using PyTorch high values to represent our objects, and they are friendly to GPU. But then user code has to know how to use it. We're not writing business logic of transformations. We're writing kind of shells so users can plug in their logic in there.
Cool. I think we're about at time, so we can continue the conversation between the talks. Thanks for the great talk.